About improper integrals today. So what is it about this first integral here that is unfamiliar to us right now? Having infinity as one of the bounds. So that asks us how much area is under e to the x between negative infinity and 0, right? So it kind of seems like the area would be infinite, right? Because e to the x goes on forever. Yeah, it looks like this. So I'm looking for all that area under e to the x from negative infinity to 0. Is it infinite? Is it finite? We will see. All right, how about if I wanted to find the area from negative 3 to 3 under the curve 1 over x squared? What is weird about that one? Turns into what? Oh, yeah, so the antiderivative of x to the negative 2 would be x to the negative 1, or negative x to the negative 1. Yeah, however, there's a little like fine print in using the fundamental theorem. Do you remember what it is? You can only use the fundamental theorem if the function that you're integrating is continuous. Yeah. On the interval. Is 1 over x squared continuous from negative 3 to 3? No. It has a asymptote at 0, right? So 1 over x squared looks like this. So this integral is asking me to find the area between negative 3 and 3. So we've got these like infinite pieces near 0. It shoots up, and like how much area is there? It's hard to say. It just keeps going up forever, right? So these are two strange integrals that both deal with an infinite area. Or an infinite interval of integration, or an infinite discontinuity within the interval is called an improper integral. So in this section, we're going to learn how to deal with these things. Remind me to encourage you to verify your answers on the calculator. So let's say, still dealing with the same function, 1 over x squared, but I just want to find the area under that curve from 1 to infinity. So the area under 1 over x squared from 1 to infinity. So just draw a line at 1, and I want all of this area under that curve forever. Okay. So how much area is there? So first what we do is we replace the infinity with some constant b. We'll say, well, let's see, you know, if I could choose any b I want. I could choose 10, 100, 1,000, right? So I'm just going to put a b there and use the fundamental theorem. So the integral from 1 to b, 1 over x squared, take the antiderivative, and I get negative x to the negative 1, evaluated from 1 to b. Plug in a b, so I get negative x to the negative b, right? And then subtract what you get when you plug in the 1, which is negative, whoops, I messed up, sorry. Negative b to the negative 1 minus negative 1 to the negative 1. So that's negative 1 over b. And 1 to the negative 1, that's 1. So this is plus 1. Okay, so what does that integral represent? the area under the curve from 1 to any constant b, right? So the area under the curve from 1 to 10 would be 1 minus a tenth, right? From 1 to 100 would be 1 minus a hundredth. So this is the area under the curve from 1 to any constant b. Okay, so what should I do if I want to find the integral from 1 to infinity? Plug in infinity for b is kind of the shorthand that people use when they mean something else, something a little more formal. Take the limit as b approaches infinity. We'll take the limit as b approaches infinity of negative 1 over b plus 1. So what happens to the fraction 1 over b as b gets really large? It gets small, it goes to 0. So my limit for this first term is 0. 1 that never changes, doesn't matter what b is. So the limit is 1. That's the area under the curve from 1 to infinity. All right, how could I use my calculator to check the answer? Calculator is a finite device. I can't plug in infinity. I can't ask it to take a limit for me. But what can I do to try to verify it? Yeah, we'll do 1 to a really large number, and then maybe a larger number, and maybe a third larger number, and see what the limit is approaching numerically. So actually, I think I'll just do it in my home screen. So I have math 9, yep. And my function is 1 over x squared, comma x, comma 1, comma, and then I'll just pick a big number like 100. I guess, I mean, of all the numbers, 100 isn't that big, but we'll see what this gets us. 0.99. Okay, so maybe we'll do it again, and we'll put in 1,000 this time. .999. Put in 10,000, and we're going to start to see that this thing is actually approaching 1. In fact, after a while, it might start to give us 1 because it just can't be that accurate. Well, 0.9999. So it looks like this is definitely approaching 1. So that's how we define an integral to infinity, right? If one of the bounds is infinity, replace your infinity with a constant, and then let the constant, then take the limit as that constant approaches infinity. So the integral from a, some constant a, to infinity of f of x dx means the limit as b approaches infinity of the integral from a to b. And if your infinity is the lower bound, negative infinity, do the same thing. Replace the negative infinity with some constant a, then take the limit as a approaches negative infinity. If the limit exists, right, if you take the limit and you get a number as an answer, we say that the integral converges. And if you take the limit and it just goes to infinity, we say the integral diverges. So in this example that we did, finding the area under 1 over x squared from 1 to infinity, there's a finite amount of area here, even though the interval goes forever. So we say that this integral converges. Finite area converges. Sometimes there's an infinite amount of area under a curve, and we would say it diverges. Okay, so let's try this one together. The integral from 3 to infinity of 1 over x dx. Looks pretty similar. The picture of 1 over x looks pretty similar to the 1 over x squared picture. So I want to find this area under the curve from 1 to infinity. So we follow the same procedure. We just take the integral from 3 to b, replace the infinity with some constant, 1 over x dx. Right? What's the antiderivative of 1 over x? ln x. So this is going to be the ln of x evaluated from 3 to b. So we've got the ln of b minus the ln of 3. So that represents the area under 1 over x from 1 to any constant b. So I just can stop it at any point and calculate that area. Then I'm just going to take the limit as b goes to infinity. So the integral from 3 to infinity of 1 over x dx is equal to the limit as b approaches infinity of ln b minus the ln of 3. I dropped the absolute value on the b because I know b is positive, so I don't need to write it. Same with the 3. I know 3 is positive. Okay, what happens to the ln of something as that something gets bigger and bigger and bigger? It gets bigger. Yeah, the natural log is an increasing function. So as b gets bigger, the ln of b gets bigger. So this goes to infinity. ln of 3 is a constant, doesn't change as b gets bigger. So this is infinity. So the area under 1 over x from 1 to infinity is infinite. That integral diverges. Different from the area under 1 over x squared, right? That area is finite and it's 1. Kind of interesting, right? What is it about the function that sometimes makes it converge and sometimes makes it diverge? Oops. Supposed to start at 3 on that one. All right, we're going to jump over this challenge for right now. Okay. So we're not going to write down the formal definition because it just looks a little messy, but hopefully this makes sense. When the interval of integration contains an infinite discontinuity, right, a vertical asymptote, replace the discontinuity with a constant, and then take the limit as the letter approaches the discontinuity. Oh, I skipped 7, sorry. 7 wasn't the challenge. Okay, let's go back. All right, so suppose we want to find the area from 0 to 1 under 1 over radical 1 minus x dx. So what's a problem in this interval of integration here? Yeah, if you plug a 1 into that integrand, you get 0 in the denominator. So we have a discontinuity. It's an asymptote. Let's actually just graph this thing so we can sort of keep an eye on the big picture. We're trying to find the area under that curve. So let's draw the curve. 1 over square root 1 minus x. And then I'm interested in the area under that curve from 0 to 1. So maybe I'll go like -1 to 2, just to see a little bit on either side. Or negative 0.5 to 1.5. All right, and then y, let's see, if I plug a 0 in there, I would get 1 over 1, which is 1. If I plug in fractions, I'm going to be taking the square root of fractions. So maybe I'll just go to 1, I think. Oops. Start there. All right, that was a poor choice. 0 to 5. All right, so you can start to see the vertical asymptote. It's kind of shooting up towards 1. So I'm just going to adjust this one more time, a little bit higher. Okay, so I'll copy this. So I'm looking for the area from 0 to 1, but at 1, I have this vertical asymptote. So I'm looking for all this area. And no matter how close I get to 1, there's still going to be like a teeny little bit more area, a teeny little bit of space between my curve and the asymptote. They never touch. So my problem is at x equals 1. Right? So instead of evaluating from x equals 1, I'm going to evaluate the integral from, instead of going from 0 to 1, I'm going to go from 0 to b. And just let b be some point before 1, right? So I'll put my b maybe right here, you know, something like that. So from 0 to any point, I can get the area very easily. There's no discontinuity. So I'm just going to go from 0 to b, and then once I have that, take the limit as b approaches 1. All right, so how do I get an antiderivative of 1 over 1 minus the square root of 1 minus x? Sure. Yep. So messing around with the integrand a little bit might jog an idea of a technique to use. U sub. Yep. Yep. What would you use as u? 1 minus x. It's a good choice of u. It's a good guess for you because it's an inside of a composition. Its derivative is just a -1, so we're not going to introduce any new x's. So that should work. So du dx is just -1, which means dx is negative du. Oops, that's supposed to be 0 to b. Okay. So now this becomes the integral from 0. Got to change my bounds too, right? U of 0, what's u of 0? 1. And u of b? 1 minus b. So I'm plugging my two bounds, 0 and b, into my function u, because those bounds, 0 and b, are x values, right? 0 and b are x values on this graph. So I have to change them to u values and make them my new bounds. So now, instead of going from 0 to b, I'm going to go from 1 to 1 minus b of u to the -1/2 negative du. I'll throw the negative over here. Okay, antiderivative of u to the -1/2. To u to the 1/2, or 2 square root u. All right, if I plug a 1 minus b in there, I get 2 square root 1 minus b, minus plug in a 1, and I get 2. Okay, so there's the integral from 0 to b. So I can get the area under the curve from 0 to anywhere. So I could go to 0.9, 0.99, 0.999, just get closer and closer and closer to 1, which would be taking a limit, right? Take the limit as b approaches 1 of that expression what happens as b approaches 1? Yeah, so what's under the square root is going to approach 0, right? You're going to end up with 1 minus 1. And 2 times 0 is 0, and 0 minus 2 is negative 2. How is that possible? Oh, I forgot the negative sign that I put right here. Thank you, Ed. So that means I should have a negative there, and a negative there, and a positive there, positive 2. All right, let's check it on the calculator. All right, so I want to find the area from 0 to 1. If I just put in 0 to 1, my calculator will give me an error, right? Because it's got this infinite discontinuity at one of the bounds. So instead, I will calculate from maybe 0 to 0.9. So y1 comma x comma 0. Let's just see. I'll just show you what happens if you try to put in the 1. Should give us some kind of an error. After it thinks for a really long time, it will realize that it can't get it because it's infinite. It is trying very hard, yeah. You're 89? Yeah, it's because yours is fancy. Oh, it tried. Wow. It gave me 1.999994424. So at some point, it just must have said, okay, I'm close enough to 1. Right? And that's really close to the exact value of 2. Sean, did your calculator actually give you 2, or did it give you an approximation? Oh, okay. So it is an approximation. It just rounded it to 2. Okay. All right. So now number 8. I'm not going to write down the formal definition because we didn't need it written formally to use it. We just used it already, right? And the formal definition just looks like it's just so much going on. Even if you just, break it down to the pieces, right? Find the discontinuity, replace it with a letter, take the limit as the letter approaches the discontinuity. Just what we just did. Okay, so let's look at A here. The integral from 1 to 2 of 1 over 1 minus x dx. Where is the problem in the interval of integration? Where's the discontinuity? At 1, right? If I plug a 1 into that function, I get a 0 in the denominator. So I can't just use FTC, right? So I'm going to take instead the integral from b to 2 of 1 over 1 minus x dx. And then I'm going to do that. And once I have that, I'm going to take the limit as b approaches 1 from which side? Remember left-handed and right-handed limits? Yeah, it's from the right, from the 2 side of 1. I could have put that over here too. Here we were approaching b from the left, right? Because b was approaching 1 from the left. And we just sort of, maybe we're taking that for granted because we drew the picture, right? So I would have written that approach 1 from the left. Yeah, you can and take the negative, yep. Okay, let's look at B. I'll leave that for you to do sometime in your free time. Integral from 1 to 4 of 1 over x minus 2 to the 2/3 dx. Where's the discontinuity here? At x equals 2. It's right in the middle of the interval. Right? So I'm going to have to set up two integrals, 1 to 2 and then 2 to 4. Add them together, and both of them I'm going to have to use a limit to deal with the discontinuity at the end point. So I'm going to rewrite this as an integral from 1 to 2. Plus an integral from 2 to 4. And then my discontinuity is at 2. So in both of these, I'm going to replace the 2 with a constant and then let the constant approach 2. Take the limit as the constant approaches 2. So this will be the integral from 1 to b. And then just take the limit as b approaches 2. And we're going to be approaching 2 because instead of going from 1 to 2, we're going from 1 to b, which is a little shy of 2. So we're going to be approaching 2 from the left. And then in this case, we're going to take the integral from b to 4. And take the limit as b approaches 2. And in this case, b is the lower bound. So instead of going from 2 to 4, we'd go from like 2.1 to 4, right? 2.01 to 4, right? Just trying to avoid, get as close to the asymptote as we can. So we'll be approaching from the right. In most cases, it doesn't really matter which direction you approach from because something's going to go to 0 anyway. But for the sake of being accurate, we'll write it down. What? Where'd the 1 come from? No, because it's a cube root. Yep. When you have a rational exponent, like a 2/3, the top is the power and the bottom is the root. So that's squared and cube rooted. That's a good question. Okay, so there's lots of problems for you to practice with. Go to it.